Imagine for a moment that you're looking up at the night sky, and somewhere out there, in the infinite darkness between the stars, something is moving. An object that doesn't follow the rules of our solar system. It came from the interstellar void, from such a distance that light from the nearest stars takes thousands of years to reach us. And this wanderer is heading our way. This is exactly the picture painted on October 28, 2025, by one of the most controversial yet influential astrophysicists of our time, Harvard University professor Avi Loeb. His warning didn't sound like panic, but rather the sober calculation of a scientist accustomed to facing uncomfortable truths. Drop a comment letting me know where you're watching from and what time it is. I want to know who's joining us on this cosmic journey. Avi Loeb is a polarizing figure in the scientific community. This Israeli-American astrophysicist, chair of Harvard's astronomy department, became famous not only for his academic achievements, but also for his willingness to propose hypotheses that many colleagues consider too bold. He's the scientist who suggested that Oumuamua, the interstellar object that passed through our system in 2017, might be artificial, possibly a probe from an alien civilization. He was criticized for it, but Loeb didn't back down. He founded the Galileo Project to search for evidence of extraterrestrial technology. And when someone like this talks about cosmic threats, it's worth listening, even if you don't agree with all his views. On October 28, 2025, Loeb published an article that quickly spread across scientific and popular publications. The main message was simple and frightening at the same time. Cosmic objects coming from interstellar space pose a real threat to life on Earth. Not hypothetical, not theoretical, real. And humanity, in his opinion, needs to seriously invest in creating settlements beyond our planet. Not for the romance of space exploration, not for scientific research, but for species survival. Loeb used the recently discovered Comet 3I Atlas as an example, the third interstellar object detected in our system. This comet was spotted on July 1, 2025, by the ATLAS telescope system in Chile. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, an early warning system for dangerous asteroids. 4 telescopes located in Hawaii, South Africa, and now Chile constantly scan the sky searching for potentially hazardous objects. And on July 1st, the Chilean telescope detected something unusual. The object was moving along a trajectory that couldn't be explained by the gravitational influence of the sun or planets in our system. Calculations showed it came from outside, from interstellar space. This was the third confirmed interstellar visitor after Oumuamua and Comet Borisov. 3I Atlas turned out to be a comet, and quite an unusual one. Observations revealed an elongated oblong nucleus and a characteristic green coma, a cloud of gas and dust surrounding the comet's nucleus. This green tint is caused by dicarbon molecules that glow when exposed to solar ultraviolet radiation. It's a mesmerizing sight, but for scientists, something else mattered more: the trajectory. Where is this visitor headed? Is it dangerous for Earth? The calculations were reassuring. 3I Atlas will pass far from our planet, posing no threat. The comet will merely glide along the outskirts of the solar system and return to the interstellar void, possibly never coming back. But it's precisely this moment, the safety of 3I Atlas specifically, that Avi Loeb used as the starting point for his warning. He said we should view 3I Atlas as a training exercise for planetary defense. Yes, this object is safe. The calculations are confirmed, the trajectory is known, there's no threat. But what about the next one? Or the object that comes in 10, 20, 100 years? Interstellar objects enter our system with unpredictable trajectories. We can't know in advance where the next one will come from or where it's headed. It's like playing cosmic roulette, where the stake is all of Earth's civilization. Loeb isn't the first to talk about asteroid danger. Scientists have been warning about potential collisions with near-Earth asteroids for decades. NASA and other space agencies have created monitoring programs, cataloged thousands of dangerous objects, and even conducted the DART mission, which successfully altered an asteroid's trajectory in 2022. But all these asteroids are members of our solar system. We know their orbits, can predict their movements centuries in advance. Interstellar objects are a completely different matter. They appear suddenly, move fast, and we might have only a few months or even weeks to react. Imagine the hypothetical scenario Loeb describes. Some future object, let's call it 4I, enters the solar system. Astronomers detect it when it's already crossed Jupiter's orbit. Calculations show that in 6 months, it will collide with Earth. 6 months is nothing for preparing an effective defense. Launching a spacecraft equipped with sufficient mass or explosives to alter the trajectory of a multi-kilometer object requires years of preparation. Nuclear charges, gravity tractors, kinetic impactors, all of this exists only in projects and on paper. Humanity would be helpless, watching as a deadly threat approaches at speeds of tens of kilometers per second. This is exactly why Loeb insists on the concept of a multi-planetary species. This isn't science fiction, not dreams of colonizing the galaxy. It's a pragmatic survival strategy. If all of humanity is concentrated on one planet, then one catastrophic event, whether it's a collision with an asteroid, a supervolcano, a pandemic, or nuclear war, could wipe us out completely. But if we have self-sustaining settlements on the Moon, on Mars, on orbital stations, then even a catastrophe on Earth doesn't mean the end of human civilization. It's like backing up data. You don't expect your computer to break, but you make a backup just in case it does. The Moon is only 3 days' flight from Earth. Underground bases could be built here, protected from radiation by a layer of lunar regolith. Water in the form of ice has been discovered in polar craters that never see sunlight. From this water, we can extract oxygen for breathing and hydrogen for rocket fuel. Solar panels will provide energy. 3D printing technologies will allow construction from local materials. Of course, life on the Moon won't be comfortable in the earthly sense, but it will be possible. And most importantly, it will be off Earth, safe from terrestrial catastrophes. Mars is a more ambitious goal, but also more promising for long-term survival. The red planet has an atmosphere, albeit thin. There's water ice beneath the surface and in the polar caps. A Martian day is almost the same as Earth's, 24 hours and 39 minutes. Gravity is 38% of Earth's, which is sufficient for long-term human habitation. The temperature, of course, is harsh, averaging minus 63 degrees Celsius. But in equatorial regions during summer, it can rise to a comfortable 20 degrees. Martian settlements could eventually become completely self-sufficient, producing food, oxygen, fuel, and construction materials from local resources. But Loeb understands that such projects require enormous investment, not millions or even billions. We're talking trillions of dollars over decades, and humanity, unfortunately, isn't particularly inclined to invest in preventing hypothetical catastrophes. We react to threats when they become obvious and inevitable, but rarely act preventively. History is full of examples. Pandemic warnings were ignored until COVID-19. Climate change was denied for decades. Tsunami early warning systems weren't built until the 2004 disaster. Space defense might meet the same fate until something terrible happens that forces us to act. And here it's important to understand the difference between two scenarios that Loeb clearly separates. The first is 3I Atlas now. The comet has been detected, the trajectory calculated, there's no threat. Everything is under control. We can calmly observe, study this interstellar object, collect scientific data. It's an opportunity to learn more about the composition of matter from other star systems, about comet formation processes, about the nature of the interstellar medium. Scientists around the world have pointed their telescopes at 3I Atlas, collecting spectral data, measuring velocity, analyzing the coma. This is invaluable information that will help us understand how our galaxy works. The second scenario is the hypothetical 4I or some future object. This one hasn't been discovered yet. Maybe its appearance is far in the future, or maybe it's already flying toward us but still too far away for us to notice. And this future object might be on a collision course with Earth. The probability of such an event is low. Astronomers estimate the chance of collision with a large interstellar object in any given century as negligibly small. But negligibly small doesn't mean zero. And when the stake is civilization's survival, even a small probability requires serious preparation. Loeb reminds us that interstellar objects can move at tremendous speeds, tens or even hundreds of kilometers per second. Oumuamua, for example, was traveling at about 26 kilometers per second relative to the Sun. At such speeds, even a small object carries colossal kinetic energy. A collision with an interstellar asteroid just a few hundred meters in size would release energy equivalent to thousands of nuclear bombs. If the object is larger, a kilometer or more in diameter, the consequences would be global. Massive fires, ejection of enormous amounts of dust and ash into the atmosphere, blocking of sunlight, sharp cooling, collapse of agriculture, famine, death of billions. Here's a puzzle that nature posed to us very recently. Throughout the entire history of human astronomy, through centuries of observations, cataloging celestial bodies, mapping the starry sky, we never noticed interstellar visitors. Thousands of comets were discovered and studied, millions of asteroids cataloged, but they all belonged to our solar system. They orbited the sun, following predictable paths, obeying the laws of celestial mechanics that Johannes Kepler derived back in the early 17th century. And suddenly, in 2017, everything changed. On October 19th, an object appeared on astronomers' computer screens that didn't fit any familiar patterns. The Pan-STARRS telescope, located on the summit of the extinct Haleakala volcano on the Hawaiian island of Maui, detected a rapidly moving point of light. Canadian astronomer Robert Warwick, reviewing the data, immediately knew something was off. The object was moving too fast and on the wrong trajectory. Initial calculations showed a hyperbolic orbit. The object wasn't gravitationally bound to the sun. It came from outside and was heading away, into infinity. By the time of discovery, it had already passed its closest point to the sun on September 9th and was receding at 87 kilometers per second. This was the first confirmed interstellar object in the history of observational astronomy. It was designated 1I 2017 U1 and given the Hawaiian name Oumuamua, meaning scout or messenger arriving first from afar. Oumuamua turned out to be surprisingly strange. Its dimensions were estimated between 100 and 1,000 meters in length, with a width and thickness of only 35 to 167 meters, an incredibly elongated shape resembling a cigar or even a pancake, according to some models. Such geometry is almost never seen among known asteroids and comets. The object had a reddish color, characteristic of celestial bodies, long exposed to cosmic radiation. But the most astonishing thing Oumuamua showed no signs of cometary activity, no coma, tail, gas, or dust emissions, even though it passed close enough to the sun for any comet to start evaporating. And yet the object demonstrated non-gravitational acceleration, as if something was pushing it. Usually this is a sign of degassing in comets, but no gas was detected. A puzzle wrapped in mystery, rushing away before scientists could properly study it. This is where Avi Loeb first entered the scene with his provocative hypothesis. In 2018, he and colleague Shmuel Bialy published a paper suggesting that Oumuamua might be an artifact of alien technology, possibly a solar sail, a thin reflective sheet created by an intelligent civilization. The object's acceleration, in their opinion, could be explained by solar light pressure on this thin structure. The scientific community met the hypothesis with skepticism. Most astronomers preferred natural explanations. Perhaps Oumuamua was evaporating hydrogen, which is hard to detect, or consisted of unusual nitrogen ice. But Loeb didn't back down. He insisted that science must consider all possibilities, even the most unusual, if they fit the observational data. This position made him both famous and a controversial figure in the astronomical community. 2 years later, on August 30th, 2019, a second discovery occurred. This time, the discoverer wasn't a professional institution, but an amateur astronomer from Crimea. Gennady Borisov, using a homemade telescope just 65 centimeters in diameter. He spotted an unusual object that was also moving on a hyperbolic trajectory. But unlike Oumuamua, this visitor behaved like a real comet, a bright nucleus surrounded by a coma of gas and dust, a long tail. Observations from the Hubble Space Telescope showed that Comet Borisov was racing through the solar system at 177,000 kilometers per hour. It was designated 2I Borisov, the second interstellar object. Scientists finally got the opportunity to study a visitor from another star system in detail, and it turned out to be surprisingly similar to comets in our system, though with some differences in chemical composition. 2 interstellar objects in 2 years. Coincidence? Or did humanity simply learn to spot them? The truth is that our telescopes and sky monitoring systems have become much more powerful precisely in recent decades. Pan-STARRS, Atlas. Other survey telescopes constantly scan the sky, automatically detecting everything that moves. Before this, interstellar objects may have regularly passed through our system, but we simply didn't see them. They're too dim, move too fast, appear unexpectedly. Statistical models suggest that at any given moment, there could be at least one Oumuamua-sized object within Earth's orbit, and throughout the entire solar system, about 10,000. We live at a cosmic crossroads through which visitors from distant star systems constantly rush. We were just blind to their presence before. And on July 1st, 2025, the third discovery happened. The Atlas telescope at the Chilean Rio Hurtado Observatory detected a new object with a hyperbolic trajectory. 3I Atlas, the third confirmed interstellar visitor. Unlike the mysterious Oumuamua, the new comet behaved more traditionally. A bright nucleus, elongated and oblong in shape, surrounded by a green coma colored by the glow of dicarbon molecules. Calculations showed that on October 29th, 2025, literally tomorrow, the comet will reach perihelion, its closest point to the Sun, at a distance of 1.36 astronomical units. That's approximately 203 million kilometers between the orbits of Earth and Mars. The comet won't come closer to our planet than 1.8 astronomical units, about 270 million kilometers. No threat, complete safety, or is there? The Hubble Space Telescope and the James Webb Infrared Telescope pointed their instruments at 3I Atlas. The data turned out to be intriguing. The comet shows unusually high carbon dioxide content, and relatively little water ice, a composition differing from most solar system comets. Carbon monoxide, carbonyl sulfide, cyanide, and even atomic nickel vapors were also detected. The rotation period is 16.16 hours. The dust mass loss rate fluctuates from 0.3 to 4.2 kilograms per second. All this data points to a comet, but a comet with unusual properties. The European Southern Observatory's Very Large Telescope in Chile also observed the object, recording giant jets of gas and dust directed toward the sun, normal behavior for comets approaching the star when solar heat evaporates ice from the nucleus surface. But even here, there's no shortage of speculation. Some observers noticed that the comet shows microscopic deceleration. Its speed is decreasing slightly, though it should be increasing as it approaches the sun. This triggered a wave of speculation in popular media and conspiracy forums. What if 3I Atlas isn't a comet, but a spacecraft regulating its speed? What if this is that very alien technology Loeb talked about in connection with Oumuamua? The scientific community, however, calmly explains the observed effects by reactive thrust from asymmetric degassing. When evaporating gases create a small braking force, this is a common phenomenon for comets, especially those rotating unevenly or having an inhomogeneous surface. Avi Loeb, however, used the appearance of 3I Atlas as an opportunity to return to his main theme. In his publication on October 28, 2025, he didn't claim that this particular comet is an alien artifact. He even acknowledged that calculations confirm its safety for Earth. But his argument was more subtle and strategically important. The very fact that interstellar objects exist that can enter our system with unpredictable trajectories means a potential threat. Not today, not tomorrow, but someday. 3I Atlas, according to Loeb, should be viewed as a training drill, as practice for a planetary defense system that essentially doesn't yet exist in a full-fledged form. To understand the scale of the threat, it's worth recalling the most famous collision in Earth's history. 66 million years ago, in spring, an asteroid 10 to 15 kilometers in diameter slammed into what is now the Yucatan Peninsula in Mexico. The collision speed was approximately 25 kilometers per second. The kinetic energy of the impact was equivalent to the explosion of about 10 billion atomic bombs dropped on Hiroshima. The asteroid didn't just explode, it instantly vaporized, turning into superheated gas. Along with it, a significant portion of Earth's crust at the impact point vaporized. The Chicxulub crater formed, 150 kilometers in diameter and 20 kilometers deep, the second largest crater on the planet. Such an amount of dust, soot, and vaporized rock was thrown into the atmosphere that the sun was blocked for months, possibly years. Surface temperature dropped sharply. Photosynthesis ceased. Plants died, followed by herbivores, then predators. 75% of all species on Earth disappeared. Dinosaurs, who had ruled the planet for 165 million years, went completely extinct, except for one branch that gave rise to birds. This was an asteroid from our own solar system, probably from the asteroid belt between Mars and Jupiter, knocked out by gravitational disturbance. But imagine an interstellar object of the same size. It could be moving significantly faster, 50, 70, even 100 kilometers per second. Kinetic energy is proportional to the square of velocity, so an object moving 4 times faster carries 16 times more energy. The consequences would be not just catastrophic, they could be apocalyptic in the full sense of the word, capable of destroying not just most species, but potentially all complex life on the planet's surface. Of course, the probability of such an event is extremely low. Astronomers estimate that large interstellar objects, a kilometer or more in diameter, pass through the inner solar system roughly once every few million years. The probability of collision specifically with Earth is orders of magnitude smaller. Earth is a tiny target in the vastness of cosmic space, but extremely low probability isn't impossibility. Over Earth's 4.5 billion year history, countless objects have fallen on it. Most were small. Their impacts left craters but didn't cause global catastrophes. Some, like Chicxulub, changed the course of evolution. And statistically, the next major collision isn't a question of if, but when. In 1,000 years? In 1,000,000? Tomorrow? Nobody knows. It's precisely this uncertainty that makes scientists like Loeb insist on preventive measures. Humanity developed a highly advanced technological civilization in just a few thousand years. We built cities, harnessed nuclear energy, went to space, created a global information network. But this entire civilization is fragile because it's concentrated on one planet. One lucky, rather catastrophically unlucky, shot of cosmic roulette, and everything could vanish. All our achievements, all culture, art, science, history, erased in an instant. It's like storing all your data on one hard drive without backups. Any system administrator will tell you, that's madness. On October 21st, 2025, an event occurred that went almost unnoticed in regular news, but held enormous significance for the history of space security. The International Asteroid Warning Network, known by the acronym IAWN, an organization approved by the United Nations and created specifically for planetary defense, officially announced the start of a special observation campaign for 3I Atlas. This was a historic moment. For the first time in history, an interstellar object was added to the list of potential threats tracked by the network. Not because 3I Atlas poses a real danger to Earth, calculations confirmed its safe trajectory, but because humanity decided to use its appearance as a training drill, as practice for systems that might someday save civilization. IAWN was founded in 2014 after a meteorite exploded over the Russian city of Chelyabinsk on February 15, 2013. That object was quite small, about 17 meters in diameter, but the explosion at an altitude of 23 kilometers released energy equivalent to 400 kilotons of TNT, roughly 30 times more powerful than the bomb dropped on Hiroshima. The shockwave shattered windows in buildings, injured over 1,200 people with glass fragments, and the most frightening part, no one saw this object approaching. It came from the direction of the sun, from a blind spot of observation systems. That same day, just a few hours later, asteroid 2012 DA14, 45 meters in size, flew past Earth at a distance of 27,000 kilometers, which astronomers knew about in advance. Two completely independent events on one day became a wake-up call for humanity. After Chelyabinsk, serious work began on creating a global planetary defense system. IAWN united astronomical observatories around the world, created data exchange protocols, developed methods for rapid trajectory assessment. In parallel, the Space Mission Planning Advisory Group, SMPAG, was created to develop methods for deflecting dangerous objects. In 2022, NASA successfully conducted the DART mission. A spacecraft intentionally crashed into the small asteroid Dimorphos, a satellite of the larger asteroid Didymos, and changed its orbit. This was the first demonstration in history of kinetic impact technology for planetary protection. The experiment succeeded. Dimorphos's orbital period shortened by 33 minutes, confirming that humanity is capable of changing asteroid trajectories if we detect the threat far enough in advance. But all these systems were developed for solar system asteroids and comets, objects with known or predictable orbits. Interstellar visitors are a completely different category. They move on hyperbolic trajectories, aren't bound by the sun's gravity, can appear from any direction and at tremendous speeds. 3I Atlas is moving at about 210,000 kilometers per hour, nearly 60 kilometers per second. That's 2.5 times faster than most solar system asteroids. At such speed, reaction time shrinks dramatically. Detecting an object, calculating the trajectory, making a decision, preparing and launching a deflection mission. All this requires months, preferably years. And an interstellar object might be detected when only a few months remain before a possible collision. This is exactly why IAWN decided to use 3I Atlas for training. The observation campaign was planned from November 27, 2025 to January 27, 2026. The goal: practice methods for tracking fast-moving, unpredictable objects from deep space, improve astrometric measurements, enhance trajectory prediction accuracy. IAWN representatives openly admitted 3I Atlas creates unique challenges for forecasting. Comets in general are difficult for precise calculations because reactive jets of evaporating gas can slightly alter their trajectories in unpredictable ways. And an interstellar comet with unusual chemical composition and high orbital eccentricity is a real nightmare for ballistics specialists. The orbital eccentricity of 3I Atlas is 6.15 plus or minus 0.117. This is the highest value among all known interstellar objects. For comparison, Oumuamua had an eccentricity of about 1.2, Comet Borisov about 3. The higher the eccentricity, the more elongated and open the trajectory. A value greater than 1 means a hyperbolic orbit. The object won't orbit the sun but will pass by and fly away forever. A value of 6.15 indicates extremely high velocity relative to the solar system, that this visitor flew through interstellar space for thousands or even millions of years before accidentally dropping by. The nucleus size of 3I Atlas is estimated in the range from 600 meters to 5.5 kilometers in diameter, a huge uncertainty related to the difficulties of observing a dim object at great distance. The coma, a cloud of gas and dust around the nucleus, reaches approximately 24 kilometers in diameter, which is fairly typical for an active comet. The green color of the coma, caused by dicarbon molecules glowing under solar ultraviolet radiation, gives the object an ominous, almost mystical appearance in photographs. Some astronomy enthusiasts and conspiracy theorists interpreted this glow as a sign of something unnatural, alien. But for scientists, a green coma is a common phenomenon. Dicarbon, a molecule of 2 carbon atoms, has been found in many comets in our system. It glows green under certain lighting conditions. More interesting was the chemical composition. Spectral analysis showed unusually high carbon dioxide content and relatively low water ice content compared to solar system comets. Carbon monoxide, carbonyl sulfide, cyanide, and particularly unusual atomic nickel vapors were also detected. Nickel in comets is rare, though not unprecedented. All this indicates that 3I Atlas formed under conditions different from those that existed in the early solar system, perhaps in a protoplanetary disk around a different type of star, with different temperature and chemical composition. This is invaluable information for understanding the diversity of planetary systems in the galaxy. On October 29, 2025, tomorrow according to Avi Loeb's narrative timeline, 3I Atlas will reach perihelion, its closest point to the Sun. The distance will be 1.36 astronomical units, approximately 203 million kilometers. That's between the orbits of Earth and Mars, a fairly safe distance. At this moment, the comet will reach maximum brightness, though it will remain invisible to the naked eye. Apparent magnitude around plus 14.6, which requires a good amateur telescope for observation. Professional observatories around the world pointed their instruments at the object, accumulating data to refine the trajectory. Maximum approach to Earth is expected on December 19, 2025, when the comet will be at a distance of 1.8 astronomical units, plus or minus 0.1, about 270 million kilometers. No threat. The comet will simply glide past and return to the interstellar abyss, possibly to another star system, or maybe it will drift eternally in the void between stars. But the comet's path through the solar system provided a unique opportunity. On October 3, 2025, 3I Atlas flew past Mars at a distance of just 0.19 astronomical units, about 28 million kilometers. In the red planet's sky, the comet reached 11th magnitude, which theoretically made it visible to powerful cameras on orbital spacecraft. The European Space Agency confirmed that its probes, ExoMars Trace Gas Orbiter and Mars Express, were observing the comet from Martian orbit. This is the first case when an interstellar object was observed from two planets simultaneously, from Earth and from Mars. Parallax measurements, comparing the object's position relative to distant star backgrounds from different observation points, allowed significant refinement of the comet's distance and trajectory. Moreover, it was planned that the Europa Clipper spacecraft, heading to Jupiter's moon, and Hera, flying to the Didymos-Dimorphos asteroid system, might pass through 3I Atlas's ion tail in late October to early November. A comet's ion tail is a stream of charged particles carried away by solar wind extending millions of kilometers. Direct measurements of this tail's composition could provide information about the interstellar medium the comet flew through for millennia, possibly even about gas and dust from the protoplanetary disk of that distant star system where it was born. This would be like studying a soil sample from another planet, only without having to fly there. The comet itself delivered the material to us. But not all observations were purely scientific. On October 22, 2025, anonymous sources at NASA reported that the planetary defense system was activated in connection with 3I Atlas. This triggered a wave of speculation in media and social networks. Some interpreted this as a sign of real threat, though official agency representatives quickly clarified, "There's no danger. The object is simply included in an intensive observation program to practice response protocols." But the rumor was already out. Conspiracy websites filled with theories that authorities are hiding the object's true nature, that the trajectory might change, that NASA is preparing for the worst-case scenario. Some even recalled the 2021 film Don't Look Up, a satirical comedy about a comet heading toward Earth that everyone ignores. Avi Loeb, of course, couldn't stay out of this discussion. He'd already earned a reputation as a scientist willing to consider the boldest hypotheses. In his October 28th publication, he didn't directly claim that 3I Atlas is an alien artifact, but hinted that the probability of such a scenario isn't zero. In some interviews, he estimated this probability at roughly 40%, based on certain anomalies in the object's behavior. For example, the so-called anti-tail, a stream of particles directed not away from the sun, like normal comets, but toward the sun. This phenomenon, though rare, has a natural explanation: an optical illusion that occurs when Earth passes through the plane of the comet's orbit, and we see the dust tail edge on. But for those who want to believe in alien ships, this was another suspicious sign. Most scientists were skeptical of the speculation. Jonathan McDowell, an astronomer at the Harvard-Smithsonian Center for Astrophysics, the same institution where Loeb works, stated directly, "This is clearly a natural comet." Real comet experts are laughing at suggestions otherwise. David Jewett from the University of California, Los Angeles, one of the discoverers of the Kuiper Belt and a leading comet specialist, published an article proving that 3I Atlas demonstrates completely ordinary comet behavior. All observed features, the green coma, unusual chemical composition, anti-tail, even weak brightness fluctuations, have natural explanations that don't require invoking the artificial origin hypothesis. But the debate between Loeb and his critics continued, drawing public attention to the topic of planetary defense. And perhaps there was value in that. Even if the debates were controversial, they made people think about cosmic threats. The idea that humanity should become a multi-planetary species isn't new. It wasn't born in the 21st century, not in the era of private space companies and visionary billionaires. Its roots go much deeper, to the beginning of the 20th century, when a Russian schoolteacher from Kaluga, Konstantin Eduardovich Tsiolkovsky, first seriously thought about humanity's future in space. In 1898, he wrote, "Earth is the cradle of humanity, but one cannot live in a cradle forever." These words became prophetic. Tsiolkovsky understood. The planet where life originated is beautiful and amazing, but it's not eternal as a refuge for intelligent civilization. Sooner or later, a moment will come when survival will require leaving this cradle. In those years, spaceflight seemed like pure fantasy, the dream of madmen. The Wright brothers would only just lift their first airplane into the air in 1903, and Tsiolkovsky was already calculating the velocities needed to overcome Earth's gravity, designing liquid fuel rockets, thinking about space stations. His contemporaries didn't understand why all this was necessary. Earth seemed infinite, its resources inexhaustible, dangers from space mythical. But Tsiolkovsky saw further. He understood that a civilization limited to one planet is vulnerable in the face of cosmic catastrophes, asteroids, comets, supernovae explosions. Spreading through space was for him not a romantic dream, but a logical necessity for the long-term survival of intelligent life. Just over half a century passed, and on April 12, 1961, Yuri Alexeyevich Gagarin aboard Vostok 1 made the first human spaceflight in history. 108 minutes, one orbit around Earth, and humanity was forever changed. Space ceased to be an unattainable dream. It became reality, albeit incredibly complex and dangerous. The space race began between the Soviet Union and the United States of America. Increasingly complex ships were launched. Cosmonauts and astronauts spent days in space, then weeks. On July 20th, 1969, Neil Armstrong and Buzz Aldrin stepped onto the moon's surface. It seemed that the next step would be a permanent lunar base, then a flight to Mars, then the asteroid belt, Jupiter's moons. The future seemed grand and inevitable, but it didn't happen. The Apollo space program ended in 1972. The last moon flight, Apollo 17, took place in December of that year. Since then, not a single person has left low Earth orbit, more than half a century. The reasons were prosaic: enormous cost, lack of obvious practical benefit, end of the political rivalry that funded the race. Space stations Salyut, Mir, then the International Space Station continued operating in orbit, but these were research outposts, not colonies. Astronauts and cosmonauts spent months in weightlessness, studying space's effects on the human body, conducting experiments, observing Earth. But no one lived in space permanently. No one was born there. Humanity remained tethered to its home planet's surface. In the early 21st century, the situation began to change. Private companies entered the space industry. Elon Musk's SpaceX, Jeff Bezos's Blue Origin, dozens of other firms around the world began developing reusable rockets, making space access cheaper. SpaceX demonstrated that Falcon 9 rocket first stages could return to Earth and be reused. technology that seemed impossible just a decade earlier. The cost of launching a kilogram of cargo into orbit began to drop. Musk openly stated his goal: make humanity a multi-planetary species, create a self-sustaining colony on Mars within the coming decades. For him, this isn't a commercial project or scientific experiment. It's insurance for civilization, a backup copy of humanity in case of catastrophe on Earth. Critics pointed to numerous problems. Mars is an incredibly hostile environment. Average temperature minus 63 degrees Celsius. Atmospheric pressure less than 1% of Earth's. The atmosphere consists mainly of carbon dioxide, unsuitable for breathing. There's no magnetic field protecting from cosmic radiation. One Martian day, or sol, lasts 24 hours and 39 minutes, close to Earth's. But a Martian year is 687 Earth days. Gravity is only 38% of Earth's, which can cause health problems with long-term residents. The flight to Mars takes 6 to 9 months depending on planetary positions, and launch windows open only once every 26 months. All this makes Mars colonization an extremely difficult task, but not impossible. The Moon, on the other hand, is just 3 days' flight away. Launch windows are constantly open. Communication with Earth is virtually instantaneous. Signal delay only 1.5 seconds round trip. In an emergency, the crew can return home in a few days. Lunar bases can be built in stages with constant supply from Earth in the early phases. Water in the form of ice has been discovered in permanently shadowed craters at the poles. From this water, oxygen for breathing and hydrogen for rocket fuel can be extracted. Solar panels in illuminated areas can provide energy. 3D printing technologies allow creating structures from lunar regolith, sintering it with lasers, or using it as raw material for concrete production. Underground lava tube tunnels, formed billions of years ago when lava cooled, can serve as natural shelters protected from radiation and micrometeorites. In 2017, United States President Donald Trump signed a directive for returning American astronauts to the Moon. The Artemis program was launched with the goal of landing the first woman and next man on the lunar surface by 2024, though deadlines were later pushed back. Unlike Apollo, Artemis was planned not as a series of brief visits, but as the beginning of a permanent presence. The Gateway Lunar Orbital Station was to serve as a waypoint. Bases on the surface, first temporary, then permanent. Resource extraction, fuel production, scientific research, and most importantly, practicing technologies for the future Mars flight. The People's Republic of China, the European Space Agency, Roscosmos, even private companies, all announced plans for creating lunar bases. The Moon was transforming from a symbol of past achievements into an arena for new rivalry and cooperation. Some critics called this a new space race, reminiscent of the 1960s. But supporters objected. This isn't a race for prestige. This is preparation for long-term survival. If humanity wants to survive the next global catastrophe, whether asteroid collision, supervolcano, pandemic, climate collapse, or nuclear war, it must have backup copies of civilization beyond Earth. Settlements capable of existing autonomously, producing food, water, energy, maintaining a population sufficient for genetic diversity. Avi Loeb, in his warning on October 28, 2025, was talking about exactly this. 3II Atlas, in his words, should be viewed as a reminder of our position's fragility. Right now, this comet is safe, but the next interstellar object might be on a collision course. And if we don't have settlements beyond Earth, if our entire civilization is concentrated on one planet, then we're risking everything. One catastrophic event, and billions of years of evolution, thousands of years of cultural development, all our achievements will vanish. Loeb wasn't calling for panic. He was calling for action, for long-term planning, for investment in technologies that will make us a multi-planetary species, not in centuries, but in decades. How many people are needed for a self-sustaining colony? This question has been studied by numerous researchers. Too small a population will lead to inbreeding problems, genetic degeneration. Too large will require enormous resources for maintenance. Various models proposed numbers from several hundred to several tens of thousands. A study by French anthropologist Jean-Marc Solankas in 2002 suggested a minimum of 110 people for a viable multi-generational colony. Other scientists cited figures from 500 to 10,000, depending on access to genetic material from Earth, artificial insemination technologies, and society's cultural and professional needs. But the main thing, such a colony must be completely autonomous, capable of producing food, processing waste, repairing equipment, educating future generations. Communication with Earth on Mars is delayed from 4 to 24 minutes one way, depending on the planet's mutual position. This means real dialogue is impossible. Colonists will be on their own. Psychological aspects are also critical. Isolation, confined space, dangerous environment, inability to return home. All this creates enormous stress. Isolation experiments on Earth, such as Russia's Mars 500 project or experiments at the HIC station in Hawaii, showed that even carefully selected crews face conflicts, depression, decreased motivation. The first Martian colonists will need not only technical skills, but exceptional psychological resilience. They'll be pioneers in the harshest sense of the word, living under conditions humanity has never before faced on a permanent basis. But if this succeeds, if the first Mars colony becomes reality, humanity will take the greatest step in its history. We'll cease being a species limited to one planet. We'll become a civilization distributed across multiple worlds, and in that case, even a catastrophic event on Earth won't mean the end. Somewhere on Mars's red desert, in the moon's underground domes, on rotating space stations, people will continue living, remembering, developing. They'll preserve knowledge, culture, history, and perhaps someday they'll return to restore their home planet. Or they'll continue moving further to Jupiter's moons, to the Kuiper Belt, to the Oort cloud, and one day, to other star systems. They'll become a truly spacefaring civilization for which interstellar distances aren't an insurmountable barrier, but simply the next frontier. When Avi Loeb talks about a training exercise, he means specific technologies and methods that humanity must develop and practice in advance, while the threat isn't yet real. Detecting a dangerous object is only the first step. What comes next? How do you change the trajectory of a multi-ton rock hurtling through space at tens of kilometers per second? This isn't a Hollywood movie plot where heroes blow up an asteroid with a nuclear bomb at the last moment. This is an extremely complex engineering problem requiring precise calculations, advanced technologies, and most importantly, time. Lots of time. The earlier we detect a threat, the better our chances of preventing it. And this is exactly why observing 3I Atlas is so important. It allows practicing methods for rapid detection and tracking of unpredictable objects. There are several main methods for deflecting dangerous asteroids, each with its own advantages and limitations. The first and most obvious is the kinetic impactor. The idea is simple. Launch a spacecraft and crash it into an asteroid at high speed. The impact momentum transfers to the asteroid and slightly changes its trajectory. If done far enough in advance, even a tiny velocity change, a few millimeters per second, will result in the asteroid passing by Earth, rather than colliding with it months or years later. This method was tested in the DART mission on September 26, 2022. A spacecraft weighing about 600 kilograms crashed into the asteroid Dimorphos, 160 meters in diameter, at a speed of 6.6 kilometers per second. The result exceeded expectations. Dimorphos's orbital period shortened by 33 minutes instead of the expected 7. The experiment proved the method works. But kinetic impactors are only effective against relatively small asteroids and only if we have years to prepare. For a large object, several kilometers in diameter, one impact won't be enough. Multiple impacts or more powerful intervention will be needed. And here appears the second method, nuclear explosion. Not blowing up the asteroid, like in the movie Armageddon, but detonating near it. A nuclear charge detonated tens or hundreds of meters from the asteroid's surface will vaporize part of its material. The vaporizing material will create a reactive jet that pushes the asteroid in the opposite direction, changing its trajectory. This method is potentially much more powerful than kinetic impact. A modern thermonuclear bomb can release energy equivalent to several megatons of TNT, millions of times more than a spacecraft's momentum. The problem is that using nuclear weapons in space is prohibited by the 1967 Outer Space Treaty. This treaty, signed during the Cold War, prohibits placing weapons of mass destruction in space. But in case of a real asteroid collision threat, the international community would likely reconsider these restrictions. Amendments are already being discussed that would allow using nuclear devices exclusively for planetary defense. Russian and American scientists in the early 2010s conducted joint theoretical studies, modeling nuclear deflection of asteroids of various sizes. Results showed the method could work, but requires precise targeting and careful control to avoid breaking the asteroid into many dangerous fragments. The third method is the gravity tractor. This is the most elegant and safe approach, but also the slowest. The idea is to place a spacecraft of sufficient mass near an asteroid and keep it there for months or years. The gravitational attraction between the spacecraft and asteroid, though extremely weak, will constantly act, slowly changing the asteroid's trajectory. The method's advantage: no physical contact, no risk of breaking the asteroid or destabilizing its rotation. The disadvantage: it takes a very long time. For meaningful trajectory change of a large asteroid, a gravity tractor must work for decades. This means the threat must be detected decades before a possible collision. For solar system asteroids, this is realistic. We can calculate their orbits centuries ahead. For interstellar objects appearing suddenly, this isn't an option. The fourth method, more exotic: solar sail or laser ablation. The asteroid is covered with reflective material or subjected to powerful laser radiation. Solar light pressure on the sail, or material evaporating under laser impact, creates constant, though weak, thrust that changes the trajectory over time. These methods remain theoretical so far. No one has tested them on real asteroids. But research continues. The European Space Agency is considering a mission to test a solar sail for deflecting small asteroids. China announced plans to create an orbital laser system for space debris protection that theoretically could also be used against small asteroids. But all these methods require one critically important condition: early detection. The more time we have between detecting the threat and possible collision, the more options we have. If 10 years remain until collision, we can use a gravity tractor or series of kinetic impactors. If 5 years, kinetic impact or nuclear explosion. If a year or less, only a powerful nuclear explosion, and even that might not work. If only a few months remain, as could happen with a suddenly detected interstellar object on collision course, humanity has virtually no options. We can only evacuate the region of predicted impact and prepare for consequences. This is exactly why early detection systems are so important. Pan-STARRS, Atlas, Catalina, Sky Survey, Space Surveillance Telescope. These and other observation programs constantly scan the sky, detecting and cataloging potentially hazardous objects. By 2025, over 35,000 near-Earth asteroids had been discovered. Of these, about 2,300 are classified as potentially hazardous, those that can approach Earth closer than 7.5 million kilometers and have diameters over 140 meters. None of the known objects pose a threat in the next 100 years, but the key word is known. There are millions of smaller asteroids we haven't yet discovered, and as the Chelyabinsk meteorite case showed, even a relatively small object can cause significant damage if it explodes over a populated region. In 2027, NASA plans to launch the NEO Surveyor Orbital Telescope, specifically designed for detecting near-Earth objects in the infrared range. An infrared telescope sees asteroids' thermal radiation, allowing detection even of dark objects that barely reflect visible light. The mission's goal: detect at least 90% of all near-Earth asteroids over 140 meters in diameter. This will significantly improve our cataloging of potential threats and provide more time for preparing defensive measures. The European Space Agency is working on its own NEOMIR mission, which will be positioned between Earth and the Sun to detect objects approaching from the blind spot, where the Chelyabinsk meteorite came from. But interstellar objects present a special challenge. They come from vast distances, from beyond the solar system, on trajectories impossible to predict. 3I Atlas was detected 4 months before perihelion. That's a relatively long time for observation and study, but catastrophically short for any defensive actions if the object were on a collision course. Oumuamua was detected only after it passed its closest point to the Sun and was receding. If it had been heading toward Earth, we would have learned too late to react. Comet Borisov was detected earlier, several months before perihelion, giving more time for observations. But there's no pattern. The next interstellar object might be detected a year or a week before possible collision. Everything depends on its size, brightness, trajectory, and simply luck. Statistics say the probability of Earth colliding with a large interstellar object during any specific century is extremely small. Astronomers estimate it as less than 1 chance in a million. That's much less than the probability of collision with an asteroid from our own solar system. But extremely small doesn't mean zero. And Avi Loeb is right about one thing. We shouldn't ignore even small probabilities when the stake is civilization survival. Earth's history is full of examples of improbable events that still occurred and radically changed evolution's course. The asteroid collision 66 million years ago probably had even lower probability, but it happened. And dinosaurs, who ruled the planet for over 160 million years, disappeared within a few years. Mammals rose in their place, ultimately leading to humans. We're the product of that catastrophe. And there's no guarantee the next catastrophe won't end our story if we don't prepare. When people look at the night sky and see something unusual, the first reaction is rarely rational. We're programmed to search for patterns, find meaning in chaos, see intention where there may be none. A green comet that arrived from the interstellar void, moving on an unpredictable trajectory, demonstrating strange behavioral features, perfect food for the imagination. And it's no surprise that the appearance of 3I Atlas spawned an entire wave of theories, from quite scientific hypotheses to outright fantastic scenarios. On social networks, conspiracy forums, popular blogs, a discussion unfolded that went far beyond academic astronomy. Some saw the comet as a harbinger of catastrophe, others as proof of extraterrestrial civilization's existence. Some simply enjoyed the spectacle, photographing the comet with amateur telescopes and sharing images online. One of the most popular theories, actively discussed in October 2025, was that 3I Atlas isn't a natural object but an alien probe or even a ship deliberately directed into our solar system. Supporters of this hypothesis pointed to several suspicious signs. First, the unusual chemical composition with high carbon dioxide content and low water content. Supposedly, this indicates artificial origin or modification. Second, the so-called microscopic deceleration of the comet as it approaches the sun, which some interpreted as a sign of trajectory correction by a propulsion system. Third, the anti-tail, a stream of particles directed toward the sun, which looked unnatural for a normal comet. And finally, the very fact that interstellar objects only started appearing in recent years. Isn't this a coordinated visit, first contact of an extraterrestrial civilization with humanity? The scientific community, of course, had answers to all these questions. The unusual chemical composition is explained by the fact that 3I Atlas formed under conditions of a different protoplanetary system, possibly around a different type of star, with different temperatures and chemical proportions. This is natural diversity, expected for objects from different star systems. The microscopic deceleration is the result of reactive thrust from asymmetric gas evaporation, a completely ordinary phenomenon for rotating comets with inhomogeneous surfaces. The anti-tail is an optical illusion that occurs when an observer sees a comet's dust tail from a certain angle, from the plane of its orbit. This phenomenon has been observed in many comets in our system, and the appearance of interstellar objects in recent years is explained not by their sudden activity, but by the sharply increased capabilities of observation systems. Telescopes became more powerful, sky monitoring programs more systematic. But Avi Loeb, as always, took a middle position. He didn't categorically claim that 3I Atlas is alien technology, but he didn't completely reject this possibility either. In interviews with various publications in late October 2025, he estimated the probability of the object's artificial origin at roughly 40%, based on behavioral anomalies, and his conviction that science should take the extraterrestrial civilization's hypothesis seriously. His Galileo project, launched after the disputes around Oumuamua, was created precisely for systematic search for evidence of alien technologies. Loeb argued that most scientists prejudicially reject such hypotheses not due to lack of evidence, but due to social pressure and fear of appearing like an unserious researcher. He compared this to the situation in Galileo Galilei's time, when the Church refused to look through the telescope, fearing to see what contradicts dogma. Loeb's critics were numerous and eloquent. Jonathan McDowell from the same Harvard-Smithsonian Center for Astrophysics, where Loeb works publicly, stated that real comet experts are laughing at suggestions about 3I Atlas's alien nature. David Jewett, who discovered the Kuiper Belt and has been studying comets for decades, published a detailed analysis showing that all observed features of the object have natural explanations. Michelle Bannister from the University of Canterbury in New Zealand called Loeb's speculation irresponsible, as it misleads the public and undermines trust in science. The dispute between Loeb and his colleagues became public, sometimes quite harsh, going beyond academic discussions. This was a captivating spectacle for the public, but a troubling sign of a split in the scientific community. Regardless of who's right in this dispute, and most evidence points to 3I Atlas's natural origin, the discussion itself served an important function. It attracted the attention of millions of people to the topic of cosmic threats and planetary defense. People who had never before been interested in astronomy suddenly began reading about interstellar objects, about asteroid deflection methods, about plans to colonize other planets. Media covered the topic widely, from serious scientific journals to tabloids with sensational headlines like "Alien Ship Heading to Earth." YouTube filled with videos analyzing every detail of 3I Atlas's trajectory. Amateur astronomers around the world pointed their telescopes at the dim green point, slowly moving against the star background. In a sense, the comet united people, making them look up and think about our place in space. History is full of examples of how cosmic phenomena spawned fear and speculation. In 1910, Earth passed through Halley's Comet's tail. Astronomers announced that cyanogen, a poisonous gas, was detected in the tail. Panic gripped many cities. People bought gas masks, sealed windows and doors. Some even committed suicide, fearing agonizing death from poisoning. Of course, nothing happened. The gas concentration in the comet's tail was negligible, and the tail itself so rarefied that Earth passed through it without any consequences. In 1938, Orson Welles' radio production, The War of the Worlds, realistically imitating news reports about a Martian invasion, caused mass hysteria in the United States. Thousands of people fled cities, called the police, believed the end of the world had arrived. Though it later turned out the panic scale was exaggerated by media, the very fact of such a reaction shows how deeply rooted the fear of the unknown from space is. In the modern era of the internet and social networks, speculation spreads at unprecedented speed. Any unusual information about a space object instantly grows theories, fake images, distorted scientist quotes. YouTube and Facebook recommendation algorithms promote sensational content because it generates more views and clicks. Conspiracy channels with millions of subscribers publish videos with dramatic music and ominous titles, claiming authorities are hiding the truth about an approaching catastrophe or alien invasion. Rebuttals from scientific organizations reach a much smaller audience. This creates information asymmetry, where fantastic scenarios get more attention than reality. But there's a positive side to this phenomenon. Mass interest in space, even if partly based on speculation, creates political and public pressure for funding space programs. When millions of people discuss a potential asteroid threat, it becomes harder for politicians to ignore this topic. Budgets for early detection systems, for research missions, for developing planetary defense technologies begin to grow. In 2005, NASA's Near-Earth Object Tracking Program budget was only $4 million a year, a laughable sum for an agency with a multi-billion-dollar budget. By 2025, this figure grew to $150 million, with further increases planned. This happened largely thanks to public awareness of the threat, which was amplified by media coverage of events like Oumuamua's flyby and 3I Atlas's appearance. So where's the line between healthy scientific skepticism and excessive panic? How do we distinguish real threats from imaginary ones? The answer, as usual, lies somewhere in the middle. On one hand, the probability of collision with a large interstellar object in a specific century is indeed extremely small. Scientists are right when they reassure the public, stating that 3I Atlas poses no danger. Trajectory calculations are confirmed by numerous independent observatories. No signs of course change are observed. The comet will safely pass by and leave the solar system. On the other hand, Loeb is also right in his main assertion. The very existence of interstellar objects capable of entering our system with unpredictable trajectories and high speeds represents a potential threat that humanity must be prepared for. Not panic, but not ignore either. Prepare. This preparation includes not only technologies for detecting and deflecting asteroids, but also strategic long-term planning. creating backup copies of human civilization on other celestial bodies, developing space industry capable of producing materials and equipment off Earth, designing life support systems for long-term space habitation. These are ambitious goals, requiring decades of work and trillions of dollars in investment. But looking at the perspective of centuries and millennia, these investments seem not a luxury, but a necessity. A civilization that doesn't prepare for improbable but catastrophic events will sooner or later face the consequences of its complacency. History has proven this again and again. While scientists argued about Three-Eye Atlas's nature and conspiracy theorists built theories about aliens, private space companies methodically worked on creating infrastructure that might one day save humanity from cosmic threats. And at the forefront of this revolution stood two figures, two billionaires with diametrically opposite but equally ambitious visions of the future. Elon Musk, with his company SpaceX, and Jeff Bezos with Blue Origin. Their rivalry, their achievements and failures defined the face of the space industry in the first quarter of the 21st century. They weren't just building rockets, they were building humanity's future, each in their own way. Elon Musk founded SpaceX in 2002 with one explicit goal: make humanity a multi-planetary species. For him, this isn't a beautiful metaphor, but a literal task. Create a self-sustaining colony on Mars, capable of surviving, even if contact with Earth is lost. Musk repeatedly explained his motivation. Life on Earth is vulnerable to numerous threats: asteroids, supervolcanoes, climate change, pandemics, nuclear war. The probability of any specific catastrophe may be low, but the cumulative risk that something terrible will happen over the next centuries is quite high. The only way to guarantee human civilization's survival is to spread it across multiple planets, and Mars, being the nearest planet with at least some suitable conditions, became the obvious target. By 2025, SpaceX had become the most successful private space company in history. Its Falcon 9 rockets performed over 100 launches per year, delivering satellites to orbit, supplying the International Space Station, launching astronauts for NASA and other agencies. Reusable first-stage technology, which once seemed like fantasy, became routine. Stages returned to Earth after launch, landed on floating platforms in the ocean or ground pads, underwent maintenance, and were used again. Some stages flew more than 20 times. This dramatically reduced the cost of space access. Launching a kilogram of payload to low Earth orbit, which used to cost tens of thousands of dollars, now cost $2,000 to $3,000. Space ceased being accessible only to governments and giant corporations. But Falcon 9 was just the beginning. Musk's main bet was Starship, a fully reusable rocket system designed for transporting large cargo and people to the Moon, Mars, and beyond. Starship consisted of two components: the super heavy first stage with 33 Raptor engines, and the Starship spacecraft itself with 6 engines. The entire system, fully fueled, weighed about 5,000 tons and could deliver up to 150 tons of payload to low Earth orbit in reusable mode, or up to 250 tons in expendable mode. For comparison, the famous Saturn V rocket that took people to the Moon could only put 135 tons into orbit. Starship was a revolution, not only in payload capacity, but in concept. Both stages returned and were reused like airplanes. Refuel, reload, launch again. Starship's development went hard. Early prototypes exploded on landing. Test flights ended in failures. Critics claimed the system was too complex, too ambitious, that Musk was promising the impossible. But SpaceX stubbornly continued testing. Each failure was analyzed, design improved, systems refined. By 2025, The company conducted several successful orbital test flights, though Starship hadn't yet become fully operational. Musk stated that the first uncrewed Mars missions could happen in 2026, in the next launch window. These missions wouldn't return. Their task was simply to prove that Starship can reach Mars and successfully land. Then, in 2028, the first crewed mission was planned, about 12 people spending several months on Mars, building initial infrastructure, a fuel production plant from the Martian atmosphere and ice, basic habitat modules, power supply systems. The plan sounded fantastic, and many experts doubted the timeline's realism. Former astronaut Garrett Reisman, now a professor at the University of Southern California and SpaceX consultant, in a September 2025 interview, noted that the technological challenges facing Starship are enormous. Perhaps the system will never work properly, or will require years of additional development. But, he added, if it works, Starship will revolutionize the entire space industry. The ability to deliver hundreds of tons of cargo in one launch will open completely new mission types. Large space telescopes, huge orbital stations, mass transportation of people to the Moon and Mars, even asteroid mining. Musk talked about Mars round-trip tickets potentially costing $100,000 to $500,000, affordable enough that many people in developed countries could afford it by selling their house on Earth. He envisioned a future where hundreds of starships fly to Mars during each launch window, and such windows open once every 26 months when planets are in optimal mutual position. Each ship carries up to 100 people. Over several decades, thousands, then tens of thousands of people could settle on Mars. By the end of the 21st century, 1 million, a self-sustaining colony producing its own food, building materials, fuel, equipment, direct democracy, self-governance, a new society free from many of Earth's problems. Jeff Bezos, founder of Amazon and Blue Origin, had a completely different vision. He didn't consider Mars a suitable target for long-term colonization. In his opinion, planets are limited resources, and gravity wells make moving from them energetically expensive. Instead, Bezos was inspired by physicist Gerard O'Neill's ideas, who in the 1970s proposed the concept of giant space stations, O'Neill cylinders. These structures, rotating to create artificial gravity, could accommodate millions of people, providing comfortable living conditions with perfect climate, no natural disasters, abundant energy from the sun. Bezos envisioned a future where most heavy industry is moved to space, where Earth becomes a preserve for housing and light industry, and trillions of people live in space settlements throughout the solar system. But unlike Musk, who focused on Mars from the start, Bezos chose a more gradual path. First step, the Moon. Blue Origin was developing the Blue Moon lunar lander, capable of delivering cargo and people to the lunar surface. The company received a NASA contract to create a lander for the Artemis 5 mission, scheduled for 2029. Goal: begin building a permanent lunar base, extract resources, especially water in the form of ice from polar craters, produce fuel for further missions. The Moon was to become a refueling station and industrial base for exploring the rest of the solar system. Blue Origin was also working on the New Glenn Heavy rocket, named after astronaut John Glenn. This rocket, smaller than Starship but larger than Falcon 9, was to become the main means of delivering cargo and people to orbit. New Glenn's first launch was planned for summer 2024, but was repeatedly delayed. The company moved slower than SpaceX, more cautiously, but Bezos emphasized that the goal isn't a sprint, but a marathon. "We're building a road to space," he liked to repeat. "The road must be reliable, durable, accessible to many." Blue Origin was also developing the Blue Ring space tug for moving cargo between orbits and the Orbital Reef Orbital Station, a concept of an orbital business park where tourists, researchers, and production modules could be housed. The rivalry between Musk and Bezos was public and sometimes caustic. Musk called Blue Origin's approach too slow, claiming humanity needs to move faster before catastrophe strikes. Bezos responded that haste leads to mistakes, that space doesn't forgive carelessness. Actually, both were right, and both were doing important work. SpaceX pushed the boundaries of what's possible, demonstrating that what was considered impossible, reusable rockets, mass launches, ambitious missions, could become reality. Blue Origin built long-term infrastructure, focusing on reliability and sustainability. The space industry needed both approaches. By 2025, other players entered the race. China announced plans to land taikonauts on the moon by 2030 and build an international lunar research station jointly with Russia and other partners. The European Space Agency was developing a moon village concept, an international settlement at the moon's south pole. India, Japan, the United Arab Emirates, all had their lunar programs. Private companies, from American Rocket Lab and Relativity Space to Chinese Land Space and iSpace, built their rockets, offered cargo delivery services, developed technologies for space industry. Space transformed from an arena of two superpowers in Cold War times into a multipolar, multinational public-private market. And this was good. The more participants, the more innovation, the faster the progress. But behind all these plans and projects stood a simple truth that Avi Loeb emphasized in his warning. Space expansion isn't just exploration and science, it's insurance, a backup copy of human civilization in case something goes terribly wrong on Earth. And events like 3I Atlas's appearance serve as a reminder that space isn't safe, that threats are real, that the time to act is now. While we have resources and technologies, tomorrow might be too late. On October 29, 2025, right on schedule as predicted by calculations, 3I Atlas reached perihelion, its closest point to the Sun. 203 million kilometers, a distance that light covers in 11 minutes. For human scale, an unimaginable expanse. For cosmic distances, almost a touch. The comet found itself in a zone where surface temperature could reach hundreds of degrees Celsius, where solar radiation hit with monstrous intensity, where any ice turned to vapor, bursting out in turbulent jets into surrounding space. This was the moment of truth for the interstellar visitor. Would its nucleus hold, or would it break into fragments, as happened with many comets that approached the star too closely? Several days before perihelion, an event occurred that added drama to the already tense anticipation. On the night of October 21st to 22nd, a powerful coronal mass ejection occurred on the Sun, a giant cloud of magnetized plasma thrown from our star's corona into interplanetary space. This isn't a rare phenomenon. The Sun constantly ejects such clouds, especially during periods of high activity. But this particular ejection's trajectory was such that it headed directly toward where Comet 3I Atlas should be. Specialists from the Solar Astronomy Laboratory of the Russian Academy of Sciences Space Research Institute quickly calculated. Collision was inevitable. The plasma cloud, one of the largest in the 25th solar cycle, should overtake the comet around October 25th. What would happen in such a collision? Would the comet's fragile nucleus be destroyed? Or would it survive? Observing the comet during these critical days was extremely difficult. The object was too close to the Sun, lost in its blinding rays. Ordinary telescopes were useless. Attempting to point them so close to the star could damage instruments and the observer's vision. But there's a special instrument for such cases: The LASCO C3 coronagraph, installed on the SOHO Solar Space Observatory, operating in orbit for almost 30 years, since 1995. The coronagraph uses a special disk that blocks the sun's bright disk, allowing observation of the surrounding corona and objects passing near the star. This was the instrument Russian scientists used, hoping to see what became of 3I Atlas after the plasma impact. The problem was that the comet was too dim for direct detection, even by the coronagraph. The signal was lost in image noise, but specialists found a solution. They applied a special processing technique. They summed 20 consecutive frames, 10 before the expected observation moment and 10 after. This approach allowed averaging random noise and revealing a weak but constant signal. And there, on the processed images, a tiny point appeared, slowly moving against the solar corona background. 3I Atlas was visible. It existed. It was moving along the calculated trajectory. The comet survived the collision with the plasma cloud. It held. The video published by the Solar Astronomy Laboratory was mesmerizing in its simplicity. On the coronagraph's black and white frames, a disk blocking the sun is visible, surrounded by the uneven glow of the corona. From time to time, bright streaks race through the field of view, plasma ejections rushing into space. And among all this chaotic activity, a barely noticeable point moves calmly, methodically, along its trajectory. Not accelerating, not slowing, not deviating, simply moving as a comet should move, obeying the laws of celestial mechanics and reactive thrust from evaporating gases. Scientists cautiously noted, the signal is exceptionally weak, so it's impossible to say anything definite about the body's condition. With a certain dose of imagination, one can discern some dynamics, even something resembling fragmentation. But with such low sensitivity, this is almost guaranteed to be false information. The main thing, the object is intact, the trajectory matches calculations. After October 25th, 3I Atlas left LASCO's field of view. The comet was moving away from the sun, but still remained in a zone where the star's brightness made observations impossible for ground-based telescopes. Astronomers announced, the next opportunity to see the interstellar wanderer will appear only in mid-November. For Moscow residents and similar latitudes, the comet will become visible from October 30th to November 17th in the morning sky, for a very short time, from 5 to 7 a.m., low above the southeastern horizon before sunrise, and only in a sufficiently powerful telescope with an objective diameter of at least 25 centimeters. Throughout November, the comet will move through the constellation Virgo, passing near the bright star Spica and the planet Venus, creating a beautiful, though accessible only to select observers, picture in the pre-dawn sky. The fact that 3I Atlas successfully passed perihelion and survived the solar plasma impact was important for understanding the object's nature. Many comets are destroyed during close approach to the sun. A classic example, Kreutz sun-grazer comets, fragments of one giant comet that broke up in the distant past. These fragments periodically approach the sun so closely that most of them evaporate completely, unable to withstand thermal and tidal stress. But 3I Atlas held. This indicated that its nucleus is sufficiently dense and strong, possibly consisting not only of loose ice, but containing a significant portion of rocky material, or, as some enthusiasts of alien hypotheses suggested, possessing some internal structure that gives it additional strength. Of course, the scientific community preferred natural explanations. Dense nucleus, high content of refractory materials, favorable shape. All this could explain the comet's survival. But speculation continued. One of 3I Atlas's most intriguing features, actively discussed in the last days of October, concerned its trajectory. The object was moving almost exactly in the ecliptic plane, the imaginary plane in which the solar system planets' orbits are located. Moreover, the trajectory was such that the comet approached 3 planets sequentially: Mars on October 3rd, Venus in late October to early November, and was to pass relatively close to Jupiter later. Some analysts calculated the probability of such random orbital alignment for an object arriving from interstellar space. The result turned out to be astonishingly small, approximately 0.005%, or about 1 chance in 20,000. This spawned a new wave of speculation. What if the trajectory isn't random? What if 3I Atlas really is a probe, specially directed to tour the solar system's planets to collect data? Another oddity was added to these arguments. 3I Atlas's orbit is retrograde. This means the comet moves in the direction opposite to the planet's motion around the sun. Most solar system objects, planets, asteroids, comets, move in one direction, clockwise when viewed from the ecliptic's north pole, because they all formed from a single protoplanetary disk rotating in this direction. Retrograde orbits are rare and usually indicate that an object either arrived from outside or was subjected to strong gravitational disturbances. For an interstellar object, a retrograde orbit isn't surprising. It didn't form in our system, so it can move in any direction. But supporters of the alien probe hypothesis claimed, for a reconnaissance craft wanting to tour all planets in one pass, precisely such a trajectory would be optimal. Moving against the general flow, the probe could quickly fly past all objects of interest, collect data, and return to interstellar space. The scientific community responded to these speculations patiently, but with growing irritation. Yes, the probability of such a trajectory is low, but not zero. In the universe, incredibly improbable events occur simply because space is huge and a lot of time has passed. If millions of interstellar objects fly into billions of star systems over billions of years, then sooner or later one of them will accidentally end up on a trajectory that looks too perfect. This isn't a sign of intelligent design, but simply statistics of large numbers. As for the retrograde orbit in the ecliptic plane, this also isn't impossible. The object could have been ejected from its home system as a result of gravitational interaction with a giant planet, fly through interstellar space for thousands or millions of years, and accidentally enter our system at such an angle. A simple coincidence, not requiring invoking extraterrestrial civilizations. But the debate was important not only from a scientific perspective, it performed an important social function. It attracted the attention of millions of people to issues of space security and humanity's future. When Avi Loeb published his warnings on October 28th, they didn't go unnoticed precisely thanks to public interest, fueled by discussions about 3I Atlas's nature. Politicians, usually indifferent to space programs, began asking questions. Journalists wrote articles. Ordinary people discussed on social networks. This created pressure to increase funding for planetary defense systems, to accelerate space exploration programs. In a sense, 3I Atlas, regardless of its true nature, natural comet or something else, had already fulfilled an important mission. It made humanity think about its future, about its vulnerability, about the need to act now, while there's still time. On December 19, 2025, maximum approach of 3I Atlas to Earth was expected. The distance will be 1.8 astronomical units, plus or minus 0.1, approximately 240 to 300 million kilometers. An absolutely safe distance, no threat. By that time, the comet's brightness will probably significantly decrease compared to the perihelion period, as the object will be moving away from the sun. For amateur astronomers, there will still be several weeks of opportunity to observe the interstellar visitor in sufficiently powerful telescopes. and then the comet will continue its path, moving farther away, slipping back into the interstellar abyss. In a few years, it will leave the inner solar system. In decades, it will pass Pluto's orbit. In centuries, the Oort cloud, the last bastion of the sun's gravitational influence. And then, infinity again. Perhaps someday, in millions of years, this comet will enter another star system, surprising local astronomers, if such exist, with its unexpected appearance, or it will drift eternally in the void between stars, cold, dark, lonely, keeping within itself the secrets of that protoplanetary disk where it was born billions of years ago. The history of life on Earth is a history of catastrophes and recoveries. Our planet, over its 4.5 billion years of existence, has experienced events that completely changed the biosphere's face. Mass extinctions happened at least 5 times in the geological record, and each of them erased most existing species, freeing ecological space for new life forms. We exist today precisely because of these catastrophes. Each opened new evolutionary possibilities. Each was a terrible tragedy for the perished species and an incredible chance for survivors. Studying these events gives us an important lesson. Life is surprisingly resilient, but specific species, specific civilizations, are mortal. Preparing for future catastrophes isn't paranoia, but wisdom, earned through billions of years of evolution. The most famous of these extinctions occurred 66 million years ago, at the boundary between the Cretaceous and Paleogene periods. This event destroyed dinosaurs, pterosaurs, marine reptiles, ammonites, and many other organism groups. The cause was an asteroid about 10 to 15 kilometers in diameter that crashed into what is now the Yucatan Peninsula, with energy exceeding billions of atomic bombs. Geological studies of the 21st century allowed reconstructing the catastrophe's chronology with incredible precision. The impact occurred in spring. This is evidenced by analysis of fish remains found in deposits dated to this moment. They contain characteristic zonal growth structures indicating the spring period. This is a small, almost poetic detail in the terrifying story of global catastrophe. Spring, a time of renewal and growth, became the time of the end for an entire epoch. The sequence of events was reconstructed from geological data from the impact site and from deposits worldwide. The asteroid entered the atmosphere at an angle of approximately 60 degrees, moving from northeast to southwest at about 25 kilometers per second. It crossed the atmosphere in a fraction of a second, not even having time to slow significantly. The impact into a shallow tropical sea created a crater 150 kilometers in diameter and 20 kilometers deep. The asteroid and a significant portion of Earth's crust at the impact point instantly vaporized, turning into superheated gas at temperatures of tens of thousands of degrees. The fireball expanded to sizes exceeding Earth's diameter if an observer were in space. The shock wave spread across the planet, causing earthquakes of unimaginable force. Tsunamis hundreds of meters high rolled across the oceans, reaching opposite shores. But the worst began afterward. Vaporized rock and enormous amounts of dust were thrown into the upper atmospheric layers. Incandescent debris thrown into space fell back across the entire planet, creating a rain of fire that ignited forests over vast territories. Smoke from global fires mixed with impact dust, creating a dense curtain blocking sunlight. Surface temperature on Earth dropped sharply. Photosynthesis ceased. Plants died first on land, then in the oceans. Phytoplankton, the foundation of marine food chains, died in enormous quantities. Herbivorous dinosaurs began to starve. Then predators, deprived of prey. oceans acidified from sulfuric and carbonic compounds falling from the atmosphere. Corals died. Ocean water temperature dropped by tens of degrees. This nuclear winter, as it's called by analogy with the hypothetical consequences of a major nuclear war, lasted months, possibly years. When the dust finally settled and sunlight returned, the world was unrecognizable. 75% of all species disappeared. Dinosaurs, who ruled the planet for 165 million years, remained only in one evolutionary branch: birds, descendants of small feathered dinosaurs who managed to survive the catastrophe thanks to small size, ability to fly, and possibly more flexible metabolism. Mammals, until that moment playing a secondary role, suddenly got a chance. Ecological niches freed after the dinosaurs' extinction began to fill. Evolution accelerated. Over the next 10 million years, mammals diversified into dozens of families, occupying all major ecological roles, from herbivores to predators, from terrestrial to aquatic and flying forms. And ultimately, 65 million years after the asteroid impact, one of these branches led to primates' appearance, and then humans. We're direct heirs of that catastrophe. If not for the asteroid, dinosaurs might have continued dominating the planet. Mammals would have remained small, nocturnal creatures hiding in burrows. Humans wouldn't exist. Or perhaps intelligent life would still have evolved, but in a completely different form. Who knows what intelligent dinosaur descendants could have become if they'd had enough time? This is speculative paleontology, the science of what didn't happen. But the lesson is clear. Catastrophes shape evolution's course. They close some paths and open others. For extinct species, it's tragedy. For survivors, opportunity. And humanity, as a species, must ask itself, do we want to be in the role of dinosaurs or in the role of mammals? Do we want to be a species that disappears when the next catastrophe comes, or a species that survives and thrives through preparation and adaptation? But the mass extinction at the Cretaceous-Paleogene boundary isn't the only example. The Permian extinction, which occurred 252 million years ago, was even more catastrophic. It destroyed 96% of all marine species and 70% of terrestrial vertebrates. This event is called the Great Dying, or Mother of All Mass Extinctions. Its causes aren't fully clear, but probably included massive volcanism, the Siberian Traps, a giant province of basaltic outpourings threw enormous amounts of carbon dioxide, sulfur, halogens into the atmosphere. Climate changed sharply. Oceans acidified and lost oxygen. Life on Earth was on the brink of complete disappearance, but it survived. Those species survived that could adapt to extreme conditions: low oxygen content, high temperatures, acidic waters, and life recovered, producing in the subsequent Triassic epoch completely new forms, including the first dinosaurs. Each of the 5 great mass extinctions in Earth's history had its own causes: volcanism, sea level changes, glaciations, possibly asteroid impacts. But they all demonstrate one pattern. Life as a phenomenon is incredibly resilient, but specific species are vulnerable. Adaptation, diversity, distribution across various habitats, these are factors that increase survival chances. And this applies not only to biological species, but to technological civilizations. A civilization concentrated in one place, dependent on one planet, is vulnerable to catastrophes specific to that planet. A civilization distributed across several worlds possesses much greater resilience. Even if one planet perishes, others will survive, preserving knowledge, culture, genetic diversity. History also teaches us that catastrophes don't necessarily come with cosmic scales. Human civilizations disappeared for many reasons. climate changes destroyed Mayan civilization in Central America. A series of droughts in the 9th–10th centuries AD led to the collapse of city-states, famine, social conflicts. Mycenaean civilization in Bronze Age Greece disappeared around the 11th century BC as a result of a complex of factors, including earthquakes, invasions, and internal conflicts. The Roman Empire, antiquity's greatest civilization, fell under blows of barbarian invasions, economic crisis, epidemics, and internal strife. None of these civilizations was destroyed by an asteroid or comet. They fell for more prosaic reasons. But all were limited to one planet, one region. Their fall was local, but seemed like the end of the world to people living in them. Modern global civilization is in some sense more resilient. Knowledge is distributed, culture is diverse, technologies are available in many regions. But in another sense, it's more vulnerable. We all depend on complex global systems, trade, communications, energy supply. Destruction of these systems can have cascading consequences spreading across the entire planet. The COVID-19 pandemic, which began in 2019, demonstrated this. A relatively moderate mortality virus, about 1% mortality, practically paralyzed the global economy, closed borders, caused social upheavals. What will happen if the next pandemic is deadlier? Or if there's a large-scale cyber attack on critical infrastructure? Or nuclear war between major powers? All these threats are real, and all can occur even before any asteroid threatens Earth. But the asteroid or comet threat is unique in that it can be prevented with technology if we prepare in advance. Unlike earthquakes or volcanic eruptions, which we can't yet predict far enough in advance or prevent, we can calculate an asteroid's trajectory with enormous precision, detect it years or decades before collision, and change it using technologies available to us. This makes the asteroid threat paradoxically more manageable than many other catastrophic risks, but only if we act proactively, not reactively. Only if we create detection systems, practice deflection technologies, prepare action plans, and only if we have backup copies of civilization beyond Earth in case something goes wrong. On the evening of October 28, 2025, when Avi Loeb published his warning about 3I Atlas and cosmic threats, most people on Earth were doing ordinary things: cooking dinner, watching TV, communicating with families, planning tomorrow. Life continued, as always. A comet flying somewhere in space at a distance of 200 million kilometers seemed something abstract, distant, unrelated to everyday life. And this is normal. Human psychology evolved to solve immediate problems: find food, avoid predators, build shelter. We're not very good at perceiving long-term, improbable, but catastrophic risks. They seem unreal until they become inevitable. And then it's too late to act. But history teaches us that long-term planning, even in the face of uncertainty, is a sign of wisdom. Ancient civilizations built irrigation systems, stored grain in case of crop failure, erected walls for protection from future enemies. They invested resources in preparing for events that might not occur in their lifetime. And precisely these civilizations prospered for centuries. Those who lived only for today disappeared, leaving behind only archaeological ruins. Modern humanity faces a similar choice, only the scale is immeasurably larger. Should we invest in space infrastructure, in planetary defense systems, in creating settlements on other celestial bodies, or continue focusing exclusively on earthly problems, leaving future generations unprotected from cosmic threats? Critics of space programs often point to more pressing problems requiring solutions: poverty, hunger, disease, climate change, social inequality. The list is long and serious. Why spend billions on rockets and space stations when this money could feed the hungry, heal the sick, build schools and hospitals? This argument has moral force and emotional appeal, but it's based on a false dichotomy, the assumption that we must choose between solving earthly problems and space programs. In reality, the global economy is large enough to do both. The entire world space budget, including government agencies and private companies, is about $500 billion per year, about 0.5% of global GDP. This is less than the world spends on advertising, less than on military expenditures, incomparably less than on healthcare or education. Space doesn't take resources from earthly programs. Rather, lack of political will and inefficient resource allocation are the reasons many problems remain unsolved. Moreover, space technologies have direct practical applications that improve life on Earth. Communication satellites provide internet and phone service to remote regions. GPS satellites are used in navigation, agriculture, rescue operations. Earth monitoring satellites track climate change, deforestation, oil spills, disease spread, helping make informed decisions. Technologies developed for space programs, from solar panels to water purification systems, from medical sensors to new materials, find application in millions of people's daily lives. Investments in space return to society many times over, though not always in directly obvious ways. And this doesn't count long-term advantages. Access to asteroid resources, space energy, scientific knowledge, inspiration, and uniting humanity around a common goal. Creating settlements on the Moon and Mars isn't a distraction from earthly problems, but their expansion. Life support technologies developed for Martian colonies, where every gram of water and every liter of air is critical, can be applied in desert or polluted regions of Earth. Closed-cycle food production methods necessary for space settlements will help solve the hunger problem on a planet with growing population and changing climate. Recycling and resource reuse systems, absolutely necessary in space, can make Earth's economy more sustainable and ecological. Space exploration stimulates technology development that then improves life on Earth. This isn't a zero-sum game where one's gain means another's loss. This is an investment in the future that benefits both now and long-term. By the end of 2025, humanity stood on the threshold of a new era of space exploration. Private companies reduced launch costs by an order of magnitude. Reusable rockets became reality. Dozens of countries and hundreds of companies participated in the space industry. NASA and its international partners were preparing to return people to the Moon. China was building plans for its lunar program. SpaceX was developing Starship for Mars flights. Private space stations were being designed for tourism, research, and manufacturing. This was a moment similar to the beginning of the Age of Discovery in the 15th-16th centuries, when European navigators set off into the unknown, discovering new continents, new trade routes, expanding the boundaries of the known world. Then, no one could predict how these discoveries would change history. Now we face similar uncertainty. How will humanity change when it becomes a multi-planetary species? What societies will arise on Mars? What new cultures, ideas, technologies will be born in space settlements? What conflicts and cooperation await us? The appearance of 3i Atlas was a reminder that space isn't an empty, static backdrop, but a dynamic, sometimes dangerous environment. Interstellar objects fly into our system. Asteroids are deflected from their orbits by gravitational disturbances. The Sun periodically ejects streams of charged particles capable of disabling electronics. Comets approach from the Oort cloud on the system's outskirts, sometimes heading toward inner planets. Space is alive, changeable, full of surprises. And humanity, living in this space on a small blue planet, must learn not just to observe these phenomena, but to actively react, defend, adapt. We can no longer afford to be passive observers. We must become active participants in the cosmic drama unfolding around us. Avi Loeb's warning on October 28, 2025, didn't contain panic or apocalyptic predictions. He didn't claim 3I Atlas poses danger. Calculations clearly showed safety. He didn't categorically insist on the object's alien nature, though he didn't exclude this possibility. His message was more subtle and strategically important. He called for viewing 3I Atlas's appearance as a training drill, as an opportunity to test our detection and response systems, as a reminder of the need for long-term planning. He called for investment in creating a multi-planetary civilization, not from fear, but from wisdom. Not because catastrophe is inevitable tomorrow, but because someday in the future, in decades, centuries, or millennia, it may occur. And whether humanity is ready for that moment or not depends on the choices we make now. When Comet 3I Atlas completes its passage through the inner solar system and returns to the interstellar void, it will leave behind not only scientific data and controversial hypotheses. It will leave a lesson, a reminder that space is full of surprises, that the safety we feel living on Earth under the protective blanket of atmosphere is an illusion, though a very convincing one, that the universe doesn't care about our survival, and we must take care of ourselves, that the time to act is now, while we have resources, technologies, and most importantly, time. The history of life on Earth shows species that adapt, spread across different environments, prepare for an uncertain future, survive and thrive. Those who stay in place, depend on one habitat, ignore warning signs, disappear, leaving behind only fossils. Which of these species will humanity become? The choice is ours, and this choice must be made not sometime in the future. It must be made today, now, with every decision, every investment, every step toward the stars. Close your eyes. Imagine the night sky in 100 years. Perhaps there, in orbit, lights of dozens of space stations will shine. Perhaps on the moon, domes of the first permanent settlements flicker. Perhaps somewhere between Earth and Mars, ships with colonists fly, heading to a new home on the red planet. Or perhaps the sky will remain as empty as now because humanity chose another path focused on the present, forgetting the future. Which of these scenarios becomes reality depends on us, on decisions made now, on understanding that we're not just Earth inhabitants, but children of the universe, and our place isn't limited to one planet. Space calls. The only question is whether we'll answer this call.